At this point, we will talk about the law of total probability. Now, you see a partition of a sample space here. Let's say this is my sample space. And when I say a partition, that's a mathematical term. That means a set of sets, let's say. And in this specific example, that is B1, B2 through B8. Okay, these are all subsets of the sample space. So essentially they are events, okay? There are two conditions for this collection to be a partition. First of all, when you unite them, you should obtain the sample space, okay? No outcome is left out. You pick any outcome that's in at least one of these events, B1 through B8, okay? And the second condition, when I and j are different, B sub I and B sub j are disjoint events. They do not overlap. So if you take any pair among these subsets, you will see no intersection, okay? No common outcomes. If you have this, we call this a partition. So essentially, you are breaking the sample space up into a certain number of pieces, okay? This is what we call a partition. Now, in this situation, assume that you have the sample space and assume that you have this particular partition. Suppose that we are interested in the probability of some event, let's call it A. Okay, let this be event A. Now in this picture, you see the intersection of event A with the sets B through B8. Okay, so B through B8 is the partition of the sample space, and A is some other event. And I'm interested in computing the probability of event A. Now, when you look at the individual intersections of the B sets with event A, now you see this one here. This here is A intersection B1, right? This here is A intersection B2. B3 itself is A intersection B3. A intersection B4 is given here. A intersection B5, and this is left out here. And B6, similar to B3, is entirely in A intersection B6. And B7 has no overlap with A, so A intersection with B7 is empty. And this here is A intersection B8. Okay, so these individual intersections, you see, they also form a partition of event A. How so? They satisfy the definition of a partition. First of all, when you unite them, they give you A, right? A intersection B1, A intersection B2, A intersection B3, A intersection B4, A intersection B5, A intersection B6, A intersection B7, which is empty, and A intersection B8 here. Unite them all together, you get A. Okay, that was the first condition. And number two, they are all disjoint because these are disjoint. So when I intersect them with A, obviously the individual intersections will also be disjoint. So it also satisfies the second condition, which means these intersections, individual intersections, they give me a partition of event A. Now, what good this is going to do to me? Let's say I'm interested in the probability of event A, but I cannot write its probability directly. To write its probability, I condition it on the B's. When it's easier to write the probability of A, when you have the information on which of the B events has occurred. Okay, let B through B sub K be a partition of S. Okay, for any event A, I can write A in this form: the union of these intersections, A intersection B sub I. Okay, and since this is a partition, these intersections, they form a partition of A, which means they are disjoint. So apply axiom number 3 to obtain the probability of A. Since these are disjoint, I can write the probability of A as the sum of the probabilities of these intersections. Okay, and this probability of an intersection can be written as the probability of a conditional probability, a conditional probability times the probability of the condition here, right? So A intersection B sub I, the probability of this event can be written as probability of A given B sub I times probability of B sub I. Okay, so this is the statement of the law of total probability. So sometimes you cannot directly write the probability of A, but it is easier to express the probability of A if you know the outcome is in which of the B events, okay? Because they form a partition and clearly one of them must have occurred. And since they're a partition, they do not overlap. The occurrence of one of them forbids the others. That's the main thing. Okay, so how do we apply it? Let's see this on a question. Suppose we have 3 urns with the following content. So in urn number 1, or let me use this side here. Urn number 1, I have, okay, I'm going to put 2 and 3 here. Right, so this is 2 reds in urn number 1 and 5 reds in urn number 2. Okay, and 3 in urn number 3. Then I have blues, 3 blues in urn number 1. Here I have just the 1. And here in number 3, I do not have any. Okay, for the whites, I'm going to use, let's use yellow. I have 5 here, 1, 2, 3, 4, 5. And here in number 2, I have 4. And in number 3, I do not have any whites, but I have 7 blacks. So that is 1, 2, 3, 4, 5, 6, 7. Okay, so this is the setup. Now the question is, I throw a fair die, okay, 1 through 6. If the outcome is 1 or 2, so I throw a die. If the outcome is 1 or 2, then I pick a ball from urn number 1. Okay. Urn number 1. If the outcome is 3, the outcome of the die, if it is 3, then I use urn number 2. Okay. Otherwise, so if it is either 4, 5, or 6, let's say otherwise, urn number 3. The question is, let me see the question. What is the probability of selecting a black ball? Okay. So this is sort of easier because you see black is only in urn number 3, and you see to select a black, I have to use urn number 3, and that happens only when I throw a 4 or a 5 or a 6. And of course, selecting a ball from the urn and the die, obviously I can assume that they are independent. There is no reason to believe there is any connection. Okay? They are physically independent, so I can assume independence here. Therefore, this is essentially, I have to use urn number 3, and the outcome should be black. Okay? And what is the probability of using urn number 3? That is 1/2, because I have the outcomes 4, 5, and 6 to use urn number 3. So that gives me a probability of 3/6. That is 1/2. I'm going to multiply that with the probability of selecting a black ball from urn number 3, right? So that is 1, 2, 3, 4, 5, 6, 7 divided by 10. Okay, so that is 7 divided by 20. Simple enough. Here I used a product rule because I assumed the result of the die is independent of how I select a ball from an urn. Okay, it just gives me the selection of the urn. So the probability is 7 divided by 20. That was easy enough, and I didn't even use the law of total probability. But let's see question number 2. What about red? Okay. So let me erase these. I'm after the probability of red now. Now you see, it's not that easy now because I have reds in all 3. Okay, so what do? Directly writing the probability of red is not that easy. I don't see a way to do that. But here at this point, I can use the law of total probability. To be able to use the law of total probability, you have to have a partition of the sample space. And in this case, my sample space will be the outcome of the die. 1, 2, 3, 4, 5, 6. And that in turn gives me the selection of the urn. So the urns will be urn 1, urn 2, urn 3. Okay? So if I condition the outcome of red on the selection of the urn, I can write this as probability of red given urn number 1 times probability of using urn number 1. Okay? Plus probability of red given urn number 2, probability of using urn number 2, plus probability of red given urn number 3 times probability of urn number 3. Well, I could have written here the outcome, well, let me use another color here. Instead of urn 1, I could have written 1, 2, and instead of urn 2, I could have written 3, and here I could have written 4, 5, 6, considering the sample space of the die, because these are equivalent events. When the outcome is 1 or 2, I will pick urn number 1. If the outcome is 3, I will use urn number 2, and otherwise I will use urn number 3. Okay? But you see, when I condition the probability of red on the selection of the urn, it immediately becomes an easier problem. Because if you tell me which urn I'm going to use, probability of red becomes obvious, right? So to write the final result, from urn number 1, selecting a red ball has probability 2/10, right? And from number 2, I have 5/10. And from this one, I have 3/10. And since obviously this has 2/6 probability, this has 1/6 probability, this has 3/6 probability, the result will be 2/10 times 2 by 6 plus this one is 5 over 10 times 1 over 6 plus 3 over 10 times 3 over 6. Okay? So you see that is 4, that is 5, they make 9, and 3 by 3 is 9. So that is 18 divided by 60. Right? So that is essentially 3 by 10. That is the probability of selecting a red in this random experiment.